Hi. In this video we're going to record for our reference here and in the future a rule that will be pretty helpful. The rule deals with the integral of 1 over z minus z naught to the nth power. Now the rule is this. If we suppose that C is any simple closed contour that encloses the point z naught, then the integral of this function around the contour C will be either 2 pi I if the exponent in the denominator is 1, or 0 if it's any other positive integer. Now we'll see in a second why this might be useful to us. We'll evaluate an integral using this rule. But first let's talk about why it should be true. We're going to make use of the principle of deformation of contours. We're going to recall that the function 1 over z minus z naught to the nth power is analytic everywhere in the complex plane except at the point z equals z naught itself. And so if I were to define a new contour, C prime, to be just the unit circle centered at z naught, then I know that the value of this integral should equal the value of this integral. You can justify that for yourself. Now because that's true, and because I can easily parameterize this, I'm going to go ahead and compute it. We're going to parameterize that circle as z naught plus e to the it, and let t run from 0 to 2 pi. And as I make that substitution in for the function, and replace dz by z primed of t dt, I can combine the e to the it's in the denominator with e to the it in the numerator. Now if the exponent in the denominator, if that n were equal to 1, they'll just cancel each other out. I'll just have the constant I integrated over the from 0 to 2 pi. That should be a real integral. And that will just turn out to be 2 pi I. Now if on the other hand n is something greater than or equal to 2, we're going to need to write this complex exponential in polar form in order to be able to evaluate it. So I will write this as cosine of 1 minus n times t plus I times the sine of 1 minus n times t. And then when I multiply through by I get this integral down here. And then taking the antiderivatives of these functions and evaluating at the endpoints, we'll see that the cosine integral turns out to be 0 because the two endpoints evaluate to the same thing. And then the sine integral is equal to 0 because both endpoints end up evaluating to 0 as well. So the contribution is 0 for this integral, and that was true no matter what n was, as long as it wasn't equal to 1. Alright, so having proved this rule, let's now take a look at a problem involving an integral. Suppose that we're asked to compute the integral of 1 over z cubed plus 2iz squared, where we're evaluating that integral along the contour C, where in this case C is the unit circle centered at the origin with radius 1. Now, we can continue in this way. We can reduce it to a problem where we can use our rule by taking the integrand, the 1 over z cubed plus 2iz squared, and writing it in terms of partial fractions. Now you probably saw something like this many times in your second semester calculus class. I'm going to let you go ahead and review on your own the rules for breaking this up. But what we'll do is factor the denominator and break it up this is the way it turns out to appear. Now as I integrate the function over C, I can go ahead and use my properties of integrals to just take the integral of each of these pieces individually. You can see I factored constants out of the individual integrals. And now I'm going to take a look at the integral around C of each of these functions. Now 1 over z is analytic everywhere except at the origin. And the origin is included in the unit circle. It's contained inside the interior of the unit circle. And so the integral around C of 1 over z should be 2 pi I. That's our rule, because the exponent on the z is just 1. So I didn't have to parameterize this at all. I could just use that rule and put 2 pi I as the value of that first integral. Now on the other hand, 1 over z squared is analytic everywhere except at 0 again, and 0 is included inside the interior of the unit circle. But because the exponent is greater than 1, I know from my rule that this integral has the value of 0. Alright, and then finally, the integral of 1 over z plus 2i can be evaluated by noting that the integrand here is analytic everywhere except at minus 2i. However, the point z equals minus 2i is not included in the interior, so this function is analytic everywhere on or inside the contour, and so by the Cauchy-Goursat theorem, that value is 0. Now combining all these different values with the coefficients, we'll end up with a final value of 1/2 pi I. And hopefully you see that if we're ever asked to find the antiderivative, to integrate a contour integral involving a rational function in terms of z, through the method of partial fractions and by using this rule, we're going to be able to evaluate it a lot more simply than we would if we had to parameterize the curves.